Hello, my name is Richard Pham. This is Lab 4 Oscillations. This is what I'll be talking for this lab. The introduction, the purpose of this lab was to use the fundamental physics principles of law conservation of energy to compare an observational and computational model of an oscillating mass spring system. The object was the mass in the spring, its environment was the air and earth. The observed model was used through tracker, the computer model was used through GhostScript, and law conservation of energy was demonstrated as total energy remained at zero, which were the results of the lab. Fundamental physics principles discussed in lab were the energy principle, which states that energy can neither be created nor destroyed, but transformed. Second law, Newton's second law, which states that system change in momentum is proportionate to the net force acting upon the system, and the position update formulas were derived through Newton's second law, the code. The lab details, so the initial conditions were the mass and spring were held at a certain point and let go, and the spring and mass system was left to oscillate for about 9 to 10 seconds. Using tracker to pinpoint the center of the mass, and the graph here shows what I got for the x and y position with time as the x coordinate, and the system was the mass, spring, and earth due to gravity, and surroundings is air. Calculations, the mass was 0.402 kilograms, and the L was 0.7 meters from the pre-lecture video. Its initial position from my tracker was negative 0.103, negative 0.652 meters. Its initial velocity was 0 because it was let go, and so use this formula here to solve for L0, which is 0.1277 meters, and here the period from observation was 1.519 seconds from these peaks of the graph, and using this formula right here, K was solved to be 6.678 newtons per meter. So coding, I plugged in the mass and the initial position here, then kept the delta t the same from the code given. These two I plugged in into the numbers from the calculations, and these all right here are solved from the formulas given for us in the class. Here being kinetic energy being 1/2 meters for times velocity squared. The potential energy of gravity is mass times gravity times change in y. Potential energy of spring is 1/2 times k times s squared, and then all that ends up being the total energy. And then these are all the initial gravity, and then force of gravity is mass times gravity, as seen here. Force of the spring is Hooke's law, so just negative k times the stretch times L hat. And then F net, or both those forces added together. This is the position update formula derived from Newton's second law, here to find the velocity and position. And these are the L and L hats calculated using the ball, the positions. The ball dot position was just the mass in the case of the lab. And then all this is just plugging the kinetic energy and the energy equations back in, and then the change is just the initial energy minus the change, or minus the final energy, or actually the final energy minus the initial energy. This is the graphs I got, and as you see here, it's pretty close to the actual model, but the problem is pretty sure that I started the frame 1 too late, which causes like the experiment to be like a bit to the left as seen here of the model. And also I did not use all the digits after the k value or and L naught or L naught value, which possibly could have led to rounding errors. And there's inaccuracy within tracker, possibly from air resistance, potential air resistance, and also could be a human error from inaccurate tracker placement. And is the energy principle satisfied? Yes, the energy principle is satisfied because as you can see here, the delta E remained at 0 the entire time, which meant that our total energy without no external work, or total energy was 0 and remained at 0 throughout the changes in energy, meaning that the energy principle is satisfied, as it states that energy cannot be created nor destroyed, so it remains at 0, but merely transformed, as you see here for the changes in energy. And the what if question, if made two separate estimates for oscillation periods, then for the x data calculated using the same method as y data from just observation between the three peaks, averaged it out, I got 1.615 seconds for the x data and 1.519 seconds for the y data, and this caused a difference in k value, as you see here, which could possibly cause the higher change here from the model in the experiment versus for the x graph versus the y graph here. And that's my lab. Thank you.